Begin where we left off, and we left off last class when we spoke all the way up until the work kinetic energy theorem. So after that, we were looking at potential energy and then potential energy stored in a spring. And then we're going to see how these topics are all related to conservation of energy. So first, potential energy is a function of what? What do you need to have potential energy? Height above some level. And it's all relative. So right now, this phone has potential energy compared to this desk.
Right.
Well, if I put it on the desk, now it's got no potential energy. But if I compare it to the ground, it has potential energy compared to the ground. If I put it on the ground, now it has no potential energy. So it's all relative to what we call a reference point or a reference line. So in this case, if we have a change in height is where potential energy comes into play. A change in height. If there's no change in height, you're going to use the work kinetic energy theorem. You're almost always going to use that if there's no change in height. The second formula for potential energy is PES. The S can stand for two things. What could they be? What does S stand for? You can use two words. Either one's fine. What does the S stand for in PES?
It's for potential energy in the spring.
Spring is one way to think of it. And the other way to think of it is stored energy. The spring stores energy. So PES is the potential energy that is stored in a spring. Now, that is a function of how much you compress or extend the spring, which is X. Remember, X is the distance compressed or stretched. I'm telling you these things in words so that if you don't know them, like if you didn't know that without me saying it, you should write it down for sure. Right? X is the distance compressed or stretched. What is K? What is K?
It's a constant.
It's a constant, good. Give me more.
Just the spring constant.
Okay, what does that mean?
It determines how strong the spring is, really.
Yeah, how rigid or strong the spring is. If it takes a lot of force to click down on your pen or your pencil, it wouldn't be logical because you're doing it every 2 seconds, right? You click your pen open or close, use it. So it wouldn't make sense to use a spring with a high K value there because you're going to have to, every time you use it, you have to put in a ton of effort. It doesn't make any sense at all. But on a car, it makes sense to have a spring that's very rigid in your suspension system. So when you hit a bump, the spring absorbs the shock real quick. It doesn't do this. Or you don't want the springs doing this and then your car is like literally going like this forever. You want the car to hit the speed bump. When it does, it should settle out real quick. So that would have a high K value. So the K value is the spring stiffness or rigidity. In a bed, before you had Tempur-Pedic beds, a soft mattress usually had low K value springs. A firm mattress, the springs had a higher K value. Firm versus soft, how much you sink into the bed. If the spring is weak, you would sink in more. Yeah.
I was just wondering, aren't probably sometimes too stiff with their springs? Like if they
Or what sometimes?
Is there suspension? Is suspension on the car or something?
Yeah, sure. Some could be what are called overdamped, where when the car actually hits the speed bump, it doesn't oscillate at all. But usually they make car suspension systems so that they're what's called perfectly damped. So that when you hit a speed bump, it settles out in the right amount of time. Over time, though, what happens to your springs? They get stretched out. So even a bicycle, like the old bicycle that had shocks on them, those shocks might not work as well anymore because the springs have gotten weaker over time. They've degraded in like quality. You have a question?
Oh, what I was going to say was, I figured it out now. But so X is the distance from its like normal.
Correct.
Length.
Natural length.
Natural length. So it's not like if it's like super stretched.
So like if you have a 3 centimeter spring and you stretch it to 4 centimeters, X is 1. 4 and the 3, difference between the 2. Now, where are all of these utilized at once? This is conservation of energy we have to look at next. So this is what we're talking about. Let's jot this down because it's not on your formula sheet. This is something you have to know and it's not on your formula sheet. Conservation of energy tells me the energy in the system before or at any point in time is equal to the energy in the system at any other point in time or after. We use initial and final, meaning at instant A and instant B. So let's think about an example of this. I want you to just close your eyes and visualize this, okay? You're on the top of a skyscraper and you kick a soccer ball off the skyscraper with some initial velocity. So you kick it, and as it leaves the skyscraper, it has velocity. It travels down and eventually hits the ground. All right, open your eyes. Think, what kind of energy did you have and when? At the top of the building, you kicked it, and then it started to fall off the building. What kind of energy? Very good. At the beginning, you gave it velocity, so there's definitely kinetic. It has height, because it's at the top of the building, so it's also potential. So the problem that I just dictated to you would start like this. Now, eventually that object falls to the Earth's surface. What kind of energy does it have the instant before it hits the ground, Leo? Just kinetic. So we did a lot with this. We did a lot with labs with this. You guys saw the roller coaster project was theoretically this. There was a lot of information. But all that matters is that you remember conservation of energy. It's not a formula on your sheet because it's not really a formula. The formula in blue is specific to the scenario that I just described to you. Again, the formula in blue describes that scenario. What if now the scenario is this, ready? A spring is compressed, an object is launched, determine the velocity when it's at 20 meters height or at 30 meters height. Well, now we have a problem where in the beginning, instead of having potential and kinetic, we just have spring energy. So an object is compressed in a spring. That's the beginning of the problem. And we want to know the velocity at a given height. Well, now we know if it's at a given height, it has height, so that's potential energy at the end. And we want to know what the velocity is at that point, so it has to have kinetic energy at the end. So that would be that scenario. So the scenario in blue and the scenario in black both come from the conservation of energy formula, which is this right here. But you're never going to really use MEI equals MEF. You're going to use a specific equation to that scenario. So you have to adjust and adapt as you go through these problems. These are the problems, honestly, that are the easiest points to take on the test. A lot of you did really well in this section, and this is a problem where I would recommend using energy for sure. Some problems you may be able to use projectile motion, like X and Y with the columns, or energy. If you can use energy, I recommend using energy. I find it's a lot easier to use energy methods than projectile motion. How about the last two formulas in this section? P equals W over T, P equals FV. Is this P pressure? I haven't been studying pressure for a long time. Is this pressure here? What is it, Klaus?
Power.
It is power. Very good, Klaus. Power is defined as energy change over time, or the rate at which work is done. Well, look, work over time. Work is energy over time. It's a rate at which work is done. Whenever you hear rate, think divided by time. So this is work over time. What are the units of work? Units of work, what are they? Joules. So this is joules per second as units, which is a watt. Remember, the unit of power are given in watts, not to be confused with the capital W for work. If the W is in the formula, it's work. If the W is after the number, it's watts. We also looked at electrical power when we looked at chapter 19 and 20. This is mechanical power here. Mechanical power is the work done over a given time period. Now, you could also calculate mechanical power if you knew the force acting on the object and the constant velocity at which the object was moving. That's an alternative way to calculate power. Now, keep in mind here, please. Look, that was capital P. You also have capital P for pressure. You also have lowercase rho, which looks like a P, for density. And then finally, look at this next section right here. We also have P to describe momentum. So P and rho and these symbols are very easy to confuse. That's why you should be writing these things down in your formula sheet about what they each mean. So this P here, this is not rho. Rho is that loop symbol. That means density. This is not density. This P is momentum. This tells us that the momentum of an object is equal to the product of its mass and velocity. And that makes sense. The more velocity an object has, the more momentum it has. The more mass it has, the more momentum it has. Let's jot this down on the side while we're sitting here so we can see this. Oops. So we can see this. Let's jot this down on the side. This is the formula for density. Okay, that's density on the right. And that V, what does that V stand for? Volume. Whereas the V in the momentum formula stands for velocity. Okay? Very different things. Many people confuse this in the last test. That's why I'm emphasizing this right now. A lot of you use P equals mv instead of rho equals m over v. All right, now, momentum is great, but really what's important about momentum is where we apply it. So the first thing we see is this delta P equals F times T. Where did you recently see this theory in action? Egg drop. Well done, Frank. Well done. Let me make a connection there. Delta P equals F times T. That's the egg drop. That's all the egg drop was. Katie, when you designed yours kind of, when it landed after the 5th floor, everybody was saying it bent down and then it came back up. So what did Katie do? She increased the time period in which her object hit the ground by allowing it to absorb the shock. Yes, it absorbs shock, but it's increasing time. If you increase time, you're therefore decreasing force. That's how you catch an egg in an egg toss. If I throw an egg at you and you go like this and try and catch it, it's going to splat. But if I throw an egg to you and you go like this and you catch it, and you take about a second to catch it instead of a millisecond or a tenth of a second when it's your hand, by taking this time to cradle the egg as you catch it, you're increasing the time period and thus decreasing the force. Because the momentum change is the same. Momentum change has to do with final minus initial momentum. So we use another way, or we write this another way, and let's go ahead and do that. We can rewrite this formula as final momentum minus initial momentum equals F times T. Because that's what change means, right? Change means final minus initial. And then since momentum is mv, I could write this as mvf, and I could write this one as mvi. And that equals F times T. So it might be more useful to jot this down on the side of your notes, because this is what you would use for the momentum impulse theory. Okay, but again, where does that come from? It comes right from your formula, delta P. Delta P is final minus initial momentum.
That's
F times T. All right, let's look at the last two equations in this section. These both relate what? Or regard what? Or written in regards to what? These last two equations here. What are they written with respect to? Why do we write these last two equations? There's a reason we write them.
Go back to that next time.
What do the last two equations involve? What do these two equations right here involve? Come on, people. It can't be one person that knows this at this point in the year. Please, don't disappoint me like that. What do these two equations involve, Theo? Conservation of? Not energy. Conservation? Okay. Of what, though? They both have mass, okay. They both involve velocity, okay. I mean, technically the second one, there's loss of energy. You could say that's friction, but that's not what's related here.
It's like with the cars, when they drive into each other, then they become one mass and add them together. But if they remain separate, then it has mass and velocity.
Yeah, so what do we call those? We call those collisions, right? And they involve conservation of?
Both have conservation of momentum.
Yeah, conservation of momentum here. So these are our collision formulas right here. These two formulas that we have are collisions. So let's talk about this one first. What kind of a collision is this one that's starred? What kind of a collision is this? What kind of a collision is the question? Us? Yeah, it's elastic. Elastic, this one. You said inelastic, right, the first time?
No, I said elastic.
Oh, yeah, then yes, it's elastic, yeah. And what do we know about elastic collisions?
They separate.
Yeah, they collide and they separate afterward. That's the key to this one. There's separation after the collision. We also know that for perfectly elastic collisions, there's no energy loss either. So I could find the kinetic energy before the collision, I could find the kinetic energy after the collision of the whole system, and those will be, the same. How about the second formula? And?
As for inelastic collisions,
And what happens with those? This is inelastic now. The second one that started with a red.
that means the two batteries that collide combine with each other. So like if two cars crash into each other and they have combined after they get separated.
Yeah, two objects collide or somehow merge. A simple example, there was a problem in your homework at one point. You're on the dock and there's a rowboat and you jump onto the rowboat and when you land on it, it starts moving in the water. Well, that's a collision problem and now you're combined afterward because you and the boat are together. So that would be an example of what we just saw right here. Now, what happens in these problems, not unfortunately, but what happens in these problems is that there's usually a loss in energy. Usually a loss in energy due to the collision itself. And it depends on the nature of the collision to understand what the loss in energy comes from. If we use Anthony's example with two cars hitting, it's because of the heat that fuses them together. They're bumpers usually. If we think about the example of you jumping on the boat, believe it or not, the energy is probably transferred into your body that's lost. Because when you land in that boat, there's a good chance that you land and your body absorbs the shock of landing, or maybe you like hit your leg. That energy that physical like pain that you feel comes from the energy that's going into your body or transferred to you. So the concept here is about collisions. One is where they collide and separate. One is where they collide and stay together. Okay? All right, next chapters. That was it up to the midterm. That was everything through the midterm. So you see everything is in red, right? And then we have these next sections. This was after the midterm. By the way, add please here. We also did Kepler's laws in this section. I don't know why I didn't add this. Let's just add that real quick. All right, that's another topic in chapter 7 that we kind of added. 7e I called it Kepler's laws. So we'll go over that also, but there was no for Kepler's laws. All right, let's look at these two formulas before we get to that point. What do these two formulas involve? What do these two formulas here involve? Yeah?
R, radius is like...
Give me the generic term for that. What kind of motion?
Elliptical.
Not elliptical, circular motion. Okay, this has to do with circular motion. So maybe it's a merry-go-round. Maybe it's a roller coaster going through a loop-de-loop. Maybe it's a planet. Maybe it's a ball tied to a cord you're swinging over your head. Maybe it's, I don't know. It could be anything moving in circular motion, right? Anything that's rotating. Now, the key is to recognize that we're given two formulas. One of them is useful, but not as useful as the other. This first formula, yeah, this will give us the acceleration of an object in circular motion, but we usually like to know what the force is. We call that centripetal. What does centripetal mean again? Centripetal.
Towards the center.
Center seeking, or towards the center. That's because the acceleration is toward the center. That's what keeps this object moving in a circular fashion. So we usually use F equals ma, but since a is vt squared over r, I can simply put here vt squared over r. Again, because that's what a actually is. Newton's laws tell me F equals ma. You're not given this formula right here on the right. So if you don't know this, you should probably jot it down right now. Again, you're not given this formula. It just comes from F equals ma though. A is vt squared over r. What is vt? What is vt? What is vt? This can't be the Anthony show, people. Come on. I know, but I'd prefer other people to actually answer too, besides Anthony. What is vt?
Cancel after this.
Yeah.
Too soon.
What do you got, Theo? vt.
Velocity, rotation.
Yes, but what's the word you're forgetting? You're right. The velocity as it rotates.
Tangential velocity.
There it is. Tangential velocity. Well done. Okay, not terminal velocity, not Theo's velocity, but tangential velocity. So tangential simply means the velocity that is tangent to the circle. And if you recall, I did many examples of this, right? Remember? If you spin something around and you let go, I think Willow, you were the example for softball. We talked about how Willow releases at the bottom of the path usually, which causes the ball to travel in this fashion. So depending upon where you release the object in circular motion, it always moves tangent to the circle when released. Okay? And then the second formula in this section was Fg equals gm1m2 over r squared. What was that about? Fg stands for Fg, force due to gravity. Well, you know what? Earlier in the year, we had a different formula for Fg. Klaus, I had this formula earlier. How can I use both of these? How's that allowed? It doesn't have to be Klaus to answer this. I'm asking in general. How can I have both formulas and they're different though? And they both equal Fg though? How is that allowed? And?
The first Fg, that's the force of gravity felt between two different masses in space. While the other...
Let's just say two different masses. They don't have to be in space. I mean, we're all in space technically. Keep going.
The other one is what we use to find the weight of an object.
On a planet. Very good. This is specifically used to find the weight of an object on any planet's surface if you know the g value of that planet. Where does the g value, little g, come from? Well, here's where it is. It's actually really obvious whether you realize it or not. Right here. There's the g value. Gm1 over r squared. Well, because look, m2 is the mass of the object. M is the mass of the object. So this little g actually comes from g times the mass of the Earth, or whatever the planet is, divided by the distance between the center of the Earth and the object, which is really the radius of the Earth, squared. So this m1 is the mass of the planet, r is the radius of the planet, g is the universal gravitational constant on your formula sheet. If you actually calculate that for the Earth, you'll get 9.81. That's where little g comes from, actually. So using this formula, you have to be on a planet, and you have to know that planet's gravitational constant, or gravitational acceleration. If you're working with any random two objects, like this desk and this chair, there's gravity between them. You can calculate it. You would need the mass of the desk, the mass of the chair, the distance between their relative centers, which would probably be here, and this center would probably be actually a point in space somewhere. That distance, you would need capital G. You'd have to figure out all those values, and you'd use that formula over there. So this is useful when you have two objects. This is useful when you have an object on the surface of a planet. Okay, I'm telling you this stuff so that you can write it down so that when you're doing math problems, you know when to use them. That's the key I find every year. On the final exam, it's the same issue. Knowing when to use what. There's a lot of material on the final exam. You need to know when to utilize which formulas. And that's the first thing that people screw up. They write down the wrong formula to just even start the problem. And then once you have the wrong formula, I really can't even give you partial credit almost. I was being nice. On the test I gave you back, a few of you guys put, instead of F over A equals F over A for the hydraulic press, a lot of you put FA equals FA. And for the continuity equation, A1V1 equals A2V2. That's good, but it's not A1F1 equals A2F2, which a lot of you put for the continuity equation. It's wrong. So you need to know which formula to physically use on every problem, so understanding when you're going to do that. So write this down, please. All right, next section. This whole chapter was about harmonic motion, vibrations, oscillations, waves. You learned about this in this class, and then where else did you learn about this? Sine, cosine. Yeah. Remember the graphs you guys have been graphing for your cosine and sine functions? Those are all waves. The sine function, yeah, it does this. Starts at the origin, has a period of 2 pi, has a height of 1, a mid-height of -1. It goes like this, right? The cosine starts up here and it drops and goes like this. Tangent, a little bit different. I don't really care about tangent actually because it's not sinusoidal. Cosine and sine have cyclical nature to them. They continue over and over. That's where this comes from. So let's start with our first formula. Fs equals negative kx. What's going on here? Fs equals negative kx. My stylus is acting up like crazy. What's the deal with this formula? What does it tell me, Katie?
What's the force of...
S stands for? spring. Very good.
And then K is that constant?
Good. And X would be then?
Distance between,
It's the same X as when you did PES, 1/2 kx squared.
those initial point of the
Yeah, the stretched length, or the length of stretch, or the distance stretched or compressed. So why is this formula negative kx?
But I forget.
At one time you actually got going in it. Why is it negative kx? Who can remember this? This is understanding the conceptual part of it, or the theory behind it.
Is it because when you compress it, the force is pushing in the opposite direction that you're pushing it?
Yeah, and what else? If you stretch it, what does it do?
It stretch, the force goes the opposite direction.
Yeah, the force applied that you apply is always opposing the spring force itself. So if I stretch the spring to the right, which way does the spring pull? Back to the left. It's always opposite that direction of the stretch. That's where the negative comes from. So if I stretch it in the positive direction, X is positive, which makes the spring force then negative. That makes sense. It's pulling back. If I push the spring in the negative direction, it makes X negative. Well, that makes the spring force push back this way. Negative makes a positive spring force. This was called Hooke's law. Hooke's law. Hooke's law. We can clearly see that Willow's board. We can see that the stretch is proportional to the force applied. Okay? And you did this in the lab. What did you guys do? You kept adding more weights to the mass, to the slotted mass. And as you added more weight to it, you saw the spring stretch further and further and further. And this is your best example of direct variation. K being the variation constant, or the constant of proportionality, you might call it in math. So X again is the stretch, K is the actual spring stiffness or spring strength. How about the next two formulas? How about these next two here? What do they discuss? Pablo, help us out here, Pablo. What does this symbol tau even represent? Tau starts with the letter T. What does T make you think of? What does it make you think of? Time. Very good. It's the time period it takes to oscillate. So, for a mass spring system or a pendulum system, which are, what's the word when they really mean the same thing? They have the exact same kind of motion and setup, even though they're not the same.
Oscillating.
They are oscillating. But a spring and a mass does this, right? And a pendulum also does this. They follow the same exact behavior. The equations are almost identical. You would say these two different scenarios are what? Yeah, like a parallelism or analogous to one another. Parallel is good. It's like a parallelism or they are analogous in nature. So in this case, we're seeing that the period of a mass spring system has to do with the actual mass itself, m, and the stiffness of the spring. If you have more mass, it's going to take longer to oscillate. Increase, because this is directly related. If the spring is stronger, it does not stretch as far. Small oscillations. Last one. The period of a pendulum is a function of its length. You saw that in the lab. If you increase the length, it takes longer, but the mass has no effect on a pendulum. So next class, which is for you guys Wednesday, we're going to start with this part. We're not